Alrighty. Well, good morning again. This is Kyle Smith. I'm with Intertech. I'm the inside sales manager here. And then with us today in Greenville, we have Jeff Hammond of GeoFlow. So this is a part of the third installment of a three-part webinar series on the GeoFlow HydroConnect buffer tank. And on the first part, we had an overview of the HydroConnect, which we did a webinar on April 6th. And then the second part was on buffer tank selection and controls. That was on April 20th. Both of those webinars were recorded and available on our Intertech YouTube channel. Today we're going to cover the pump selection pressure drop calculations. And today, if you have any questions, please feel free to contact Intertech's Inside Sales team at 618-664-9010 today or any other time. So today, get the most out of this webinar. Please take notes. Ask questions. You'll see on the control panel on the right-hand side of your screen, you'll see an area with a tab called Questions. Please feel free to check those or use the chat function on the bottom. Then research and review during the webinar or after. With that, I'll go ahead and give it to Jeff to get started today.
Thanks, Kyle. I appreciate everybody attending the third part of the HydroConnect series. As Kyle mentioned, we'll talk about pump selection for the HydroConnect tank as well as for the heat pump. So the first part of this webinar is load piping and pump selection. You can see here by the red outline box. The first part we'll talk about the pump between the water-to-water heat pump or combo unit and the buffer tank. And then the second part of this webinar we'll talk about pumping on the other side of the tank. And there are a couple of different options that we'll look at there. So we'll start with the pressure drop calculators. If you're not already signed up for the free calculators on the GeoFlow website, if you go to www.geo-flow.com and click on the Design Calculators link, you'll be able to sign up for these free calculators. So we'll be using calculators today for all of the sizing. You could certainly do it by hand, but this just makes it much quicker. We're looking at the hydronic calculators for the applications we're talking about today. And the first one, part one of this webinar, is the load side pumping. It's called the heat pump load side pressure drop calculator. This is what the calculator looks like. It's color coded like the other calculators on the website. So you can see here the blue piping is the hard piping from the tank over to, in this case, a hose kit. This could be hard piped all the way, certainly, but in this case we have a hose kit in the example. And you'll just pick those with drop-down boxes and entries below the picture. First thing we need to do, though, is get the pressure drop of the heat exchanger on the load side of the heat pump. And I've circled full load capacity. This is a two-stage water-to-water heat pump. It's a 5-ton Intertech model. And in this case, you can see here at our temperature of 85 degrees on the load side, this is the side that connects to the buffer tank, we have a pressure drop of about 12.1 feet at 15 gallons per minute. Now there are other temperatures we could use, but we want to look at the worst case scenario. So as you see here at 110 degrees, the fluid is less viscous, so the pressure drop's lower, but we need to make sure that we size the pump for the worst case scenario. In this case, the 85 degree temperature would be when we're in the spring and the fall, and maybe we have our outdoor temperature setting at a lower water temperature, so we need to make sure we can pump in that condition as well. And also the full load capacity is our full flow when that heat pump is in full load capacity. So even though it may run in part load, we need to make sure we have a pump large enough for the full load capacity and the lower water temperatures. All right, so here's our entry screen for that calculator. I've picked, in this case, propylene glycol. You might have just water, but in this case we have some propylene glycol antifreeze. This is the flow rate of the 5-ton heat pump, the nominal flow. And this 12.1 came from the catalog that I just showed on the previous slide. In this case, we picked a hose kit. I like to use a hose kit simply because it already has PT plugs and it gives you that flexibility. So there's some vibration isolation as well. We have the length of the hose kit on one side. We've picked some ball valves from the picture, and then we have piping. In this case, PEX is the piping that connects to the hose kit over to the buffer tank. So just a handful of entries, not too many to enter here for the load side. It's just the piping between the heat pump and the buffer tank. And our results down at the bottom, you can see we come up with about 18.1 foot of head at our nominal flow rate at 15 gallons per minute. So with this number, we're now ready to size a pump. And we go back to the calculators, and we're going to pick the pump sizing calculators, the red outline. And now I'm going to pick pump sizing. It shows flow centers, but this is also for insulated pumps. The flow center has the three-way valves, which we need on the ground loop side, but between the heat pump and the buffer tank, we really just need an insulated pump. I have a picture of an insulated pump at the bottom, so you can see what we're looking at here. This is a Grundfos pump in an insulated cabinet. So if we are using chilled water, that insulation is helpful to avoid condensation. So the number here, this 18.1, came from my pressure drop calculations, and I know the flow rate, so all I have to do now is select a pump. It's important that I pick a pump that is compatible with chilled water applications, and I'll get to that later on. In this case, I'm picking a UPS 2699 on high speed. I could select medium or low as well, but I'm going to start with high and see where we end up. All right, so the output of the pump sizing calculator shows we have about 15.4 gallons per minute, so we're certainly in good shape with our requirement of 15. So in this case, one single pump is going to take care of the flow rate between the heat pump and the buffer tank. And you can also see here it gives us our average power consumption. So if we want to compare constant speed pumping to variable speed, the nice thing about this water-to-water heat pump is it's two-stage. So a lot of the year we'll be operating on part load, so we have higher heat pump efficiencies, but we don't need as much flow. So let's take a look at what variable speed might do for us. We could pick a variable speed pump, and now you notice from 185 watts we're down to 43 watts, and that's simply because we're running most of the year on part load. So this is an example of two different selections for even on the load side. On the ground loop side, you're already familiar with variable speed pumping for the flow center, but we could do the same thing on the load side pumping as well. All right, so we have part one taken care of. That's a fairly straightforward calculation, the piping from the heat pump to the buffer tank. Now we go back to the hydronic calculators, and we need to size pumping for the hydronic side of the tank. All right, we're going to pick radiant floor fan coil pressure drop calculator as our next choice. And here's a picture of the top part of that calculator. You can see the buffer tank as well as the connections to the various zones. HydroConnect is capable of up to 6 zones in its current configuration, so this shows all 6 zones. You can use anywhere from 1 to 6. You can also use either radiant zones or fan coils depending upon what the configuration is. There are a number of entries. This is a screenshot of the calculator. The first thing you want to look at is the type of system it is. We already have the antifreeze keyed in here. In this example, we're using 25% propylene glycol. We could use 20%. We could use water. Depends on the system. So my choices here are circulators for each zone, which would be a small little circulator pump for each of the manifolds, or I could use a zone valve at each manifold and use variable speed pumping. So that's one of the first things we'll talk about. The rest of these inputs are specific to each of the piping that goes to each of the zones. All right, so these are the two pumping options. If we use a variable speed pumping system, we'll have a zone valve that opens and closes as that zone is calling. So when the thermostat calls, the zone valve opens, and that tells the variable speed pump to increase RPMs to provide flow necessary for that zone. Or we could also have a small circulator at each of these zones. And the same thing, the thermostat's going to tell that zone that it needs heating or cooling, if it's the case of a fan coil, heating in the radiant floor example here, and that little circulator pump then would be energized. So this is the, you saw the inputs earlier on the slide. This is the output of that calculator. In this case, I've picked a pump for each zone. So the output will be different than if I picked variable speed pumping with zone valves. In this case, it shows me all 6 zones pressure drop. Here's my foot of head and flow rate for each of these zones. And I'll use zone 5 as my example for pump sizing in this case. The output also shows you the volume. So if we want to size an expansion tank for this system, it tells us the gallons of the system. We would add in the buffer tank capacity. In this case, if it's a hydronic tank, it would be 50 gallons. So we'd use 153.8 gallons for our expansion tank sizing. But let's do the pump sizing first for zone 5. We again go back to the pump sizing calculators. And we go to pump sizing for up to 100 gallons per minute. Again, this says flow centers. It's also insulated pumps. And I'm going to try the low speed for this zone since we don't have very much flow or head necessary. So we'll try this UPS 2699. This is a 3-speed pump, so we're going to try it in low speed. And the reason we're picking this pump, I mentioned earlier that we do have to be careful that we have a pump that's rated for chilled water. A couple of things that are important with pumps that are rated for chilled water. Number one are what we call weep holes or drain holes. In this picture, you can see a little slot, and here's a large view of that. In this particular pump, we have 3 locations, so we can rotate the pump head so that the terminal box is either in the 12 o'clock, 6 o'clock, or 9 o'clock position, and that gives us the appropriate drainage location. If we do have any condensation forming when we're using chilled water for a fan coil, for example, this drains any condensation that might form. But the second thing that's important is pumps that are rated for chilled water have coated windings, and it may be that the same Grundfos pump, it may even have the same series, a 2699 for example, might not be rated. So we do have to make sure that it's a current or it's a chilled water rated pump. I just saw a text that somebody has lost video, so I'm going to continue to talk. It looks like we still have it here in Greenville, but this will be recorded. If for some reason you're missing the video portion of it, you'll be able to log on later on and view this presentation. So if you've lost video, I apologize for that. Hopefully you can watch it later on if you have. In the case of the pumps, we do want to make sure we have one that's chilled water rated. An example here at the bottom of this slide, if we were to use a 1558, that's perfectly fine for hot water, but it doesn't have the coated windings or the weep holes, so we have to be careful with that if we are using chilled water with a fan coil. All right, so here's the output. I keyed in the 6 gallons per minute at 10.8 foot of head, and you can see here we're in fine shape even on low speed with this particular zone. One final check, we'll repeat this for each of the zones, but then we want to also make sure that we can get the full flow rate if all 6 zones are operating. Keep in mind when we're using a circulator for each of these zones, we have parallel operations. So each of these pumps are in parallel, and that means we only have the head of one pump. We might have the flow, 6 times the flow, but we're only going to have the head of one pump. So to find out what that number is, we simply add up the flow rates, which is 21 gallons per minute, and then we take the highest pressure drop of these zones. In this case, it's 16 foot of head. So we've gone back and we've sized a pump for each zone. Now we need to make sure that those pumps can perform if all 6 zones are operating. So we want to look at 21 gallons a minute and 16 foot of head. Now this is a chart from the installation manual, or you can find it online. And this shows the various little Grundfos circulators. This is a 26116, a 99. These 3 curves here are the 3-speed pump. Now with pumps in parallel, we take the number of pumps times the flow rate. So with 6 pumps in parallel, this 1 gallon per minute becomes 6, 2 gallons per minute becomes 12, 3 is 18, and so forth. If this were only 2 pumps, we'd have 2, 4, 6, 8, and so forth, all the way up to 10 gallons per minute. So the key is, with parallel pumping, we have the flow times the number of pumps, but we still only have the head of 1 pump. So that's where we have to do this double check to make sure that if all 6 zones are running, we still have enough head to provide the adequate flow. And in this case, you can see here at 21 gallons per minute, 16 foot of head, even on low speed, if all 6 pumps were set on low speed, we would still be able to easily provide 21 gallons per minute. So we're in good shape here. And in fact, most systems are going to have different flow rates for each of the zones. So my note here in the corner, when you're starting up the system, you do want to make sure that you balance the system. There may be some that need zones on low speed, some medium, some high speed, and that can be adjusted with all of the zones running. The nice thing about hydronics is that even if we're not quite on flow, maybe we're off by half a gallon per minute or something like that, all that happens is our delta T changes. So a little bit lower flow just means a higher delta T, a little bit higher flow means a little bit lower delta T. It's not the same problem we have on the heat pump side. If we have too low flow on the heat pump side of the load connections, then we could create refrigeration problems. But we're just simply talking hydronics on this side of the system. All right, so let's take a look now at the other option. I mentioned earlier when we're sizing pumping for the hydronic side of the tank, we can pick a circulator per zone, or we can pick a zone valve per zone, and then we use a variable speed pump, central pump. So in this case, I've picked variable speed pumping with zone valves, and the output is going to look different now. Instead of having pressure drop for each zone, we have a single pressure drop for all of the zones. In this case, we have 21 gallons per minute at 23.9 foot of head. And there's some assumptions here based on piping size. So we've picked a zone valve based upon the actual piping size that you chose in the calculator. So you do want to make sure that if you do use a different valve CV than the assumption, you'll want to adjust for that in the additional pressure drop section. In this case, we'll assume everything is as selected. So we'll use this number, 21 gallons per minute at 23.9 foot of head, to size our variable speed central pump. We again go back to pump sizing calculators. And I'm going to start with the same place we were earlier, the smaller pumps. And we're going to choose a variable speed pump here. So here's our variable speed Magna Geo. This is actually the same pump that you see on a flow center, variable speed flow center. So it's a less expensive way to go than a larger differential pressure type. It does need a controller. This is the same controller again on your flow center, and we'll use this in delta T mode. So temperature difference will tell that pump to speed up and slow down. In this case, it's mounted in an insulated box, so we could use it for chilled water as well if we had fan coils in the system. So I key in my 21 gallons per minute at 23.9 foot of head. I pick the variable speed pump. And now I go to the output. You can see here I'm at 21 gallons per minute at 23.9 foot of head. Now I could actually produce more, but because it has a controller, it's going to back the RPMs down on that pump to actually deliver the maximum flow rate that we need. If less than 6 zones are calling, it's going to slow that down even more, and it may be 10 gallons per minute or 6 gallons per minute or whatever the particular load is at the time. So we can actually use one of these small Magna Geo pumps for the entire system in this case. That's with delta T. If you want differential pressure mode, then we have to go to the Magna 3, and that's the next slide. The Magna 3 has a built-in pressure differential sensor, and really it doesn't make a lot of difference which way you go, delta T or differential pressure. I like the delta T on the smaller pumps because they're less expensive, number one, but it's also a product that's more readily available because it's a flow center pump, so it's more likely to be in stock, shorter lead times, and it's a little bit easier to control with the external controller. So if we want to go with the differential pressure, and this would be the case typically of a larger system. I only had a 6-zone system, but maybe we have higher pressure drop, higher flow rates, what have you, maybe more zones. then the Magna 3, you can see here, it also has an insulated cabinet like the other pump, but this has a lot more features. This is more of a commercial grade pump, so it has inside this cabinet a pressure sensor, actually a differential pressure sensor. It's positioned between the suction and the discharge of the pump, and the wire connected to it, you can just barely see it here at the bottom of the screen. This wire connects from the sensor over to the pump head. Now, instead of regulating based upon delta T, it's going to regulate based on differential pressure. So as the zone valves open and close, then the pump will speed up and slow down accordingly. So let's size this pump. We have 21 gallons per minute at 23.9 foot of head. I picked the smallest available Magna 3 currently. Right now the 40 series is our smallest available Magna 3, and that's the other reason we went with the Magna Geo in delta T mode on the previous example, because the Magna 3 is somewhat limited in size. It's really designed more for larger applications. All right, so we have our output just slightly under 21 gallons per minute. We're at 20.6. It's not really worth going up to the next size pump to get that 21 gallons per minute. We're only off by 0.4 GPM. Now, we are using a little bit more power than the Magna Geo. It was about 45 watts, if I remember right. On the Magna 3, we're about 110 watts on average, up to as much as 223. So again, this is really more for larger systems. Nothing wrong with it, certainly on a small system, because it will adjust as the zones open and close, but we can choose that based on the actual application. All right, so that's a quick overview of what we're looking at for HydroConnect pump sizing, and I'll let Kyle take over from here, and then we certainly have time for questions.
Excellent. Thanks, Jeff. So we'll take a few seconds here and allow everybody to get their questions in on the sidebar there. But in the meantime, please take some time to give us a call for some to talk about the HydroConnect one-on-one on an upcoming project, or any other project for that matter, and contact us at 618-664-9010, or email us those plans or questions at insidesales@intertechgeo.com. Just let us help in any way we can. And then, did you know that we have a design service team that's absolutely free? Hydronic work, we can do anything from the piping layout to the load to geoanalyst report and a full proposal to hand over to the customer. This webinar has been recorded and will be available on our YouTube channel. And let's see if we have any questions here, Jeff.
Okay, we'll give people just a few minutes. It looks like we have a question here on delta T control. The question is, how does delta T control? How does it keep the pump from deadheading? And the controller actually has an input. So on the HydroConnect control panel, you have a closed contact that tells that pump to start running. And so as soon as one of the zone calls, then one of the zones calls, it actually closes that contact. It tells the controller, hey, I need flow, and the controller starts looking at delta T. Now the controller automatically starts that pump at a higher flow rate just to give it time for the thermistors to react, and then after 2 minutes it starts adjusting based upon delta T. So delta T is a very effective way to control it, and so is differential pressure. A lot of times it's more of a preference than anything else. Some pump manufacturers promote delta T, some promote differential pressure. So good question. I'll wait around here for just a few more minutes if we have any other questions. Okay. Well, thank you very much for attending. As Kyle mentioned, if you think of questions afterwards, make sure you contact the Intertech Design Services team. And hopefully these three seminars have been helpful. It is recorded if you want to watch it on the Intertech YouTube channel, and certainly let us have any feedback that you might have. Thanks again.